invitation to talk. So this is actually my first Southeastern lead theory workshop, and I started at College of Charleston this last fall. And when I got the job at College of Charleston, I told one of my colleagues who was working at Reed College at the time, Veronica Chalatenko. She's a former partial student, so some of you might know her. And when I told her I got this job, I was expecting her to say, like, congratulations on getting the job. And she just got really excited suddenly and said, you're going to be a Southeast lead theory person. So you come highly recommended. And so far I'm having a great time. Okay, so this is joint with Jonathan Kujawa, Muth, and Jieru Zhu. So this is actually, we're funded by the AIM Square program. So this is a grant that flies you out to the American Institute of Mathematics headquarters every year. I think they do 3 years in a row right now. And they give you a week to work on math together, which has been a lot of fun. Actually, so AIM is in the process of moving to the Caltech campus. Right now they have been in Fry's Electronics corporate headquarters, but Fry's closed. So this is now just like some abandoned corporate building where this tiny corner is locked off for AIM. And if you explore the building, you can find some weird stuff. So there's this robot just like down the hall from where AIM is. I haven't been able to get any explanation for where this came from, but I don't know, it looks like something out of a sci-fi movie. I think maybe it came out of an old Fry store or something like that. Okay, so here's kind of the outline of the talk. So the first thing I want to talk about is webs. These are sort of the star of the talk, and I'm going to start by doing sort of a basic version of webs, which is webs for GLN. Then I'll talk about some representation theory, do some superalgebra deformations, and then talk about some of our results. And if I get time, I'll tell you what else we're planning for this square project. Okay, so what's a web diagram? So what you do is you take some parallel strings of varying thickness. So thicknesses are labeled by natural numbers or non-negative integers. You can see I've got some strings of thickness 1, 2, 1, 3, 1, and 4. And I tried to make the higher numbers slightly thicker than the lower numbers. But so then what you do is reading from bottom to top, you start merging and splitting them. So I don't know, maybe you could merge some strings like that, or there's a split. And then maybe just some merging. And whenever you decide you don't want to merge and split anymore, you stop, and you call that web diagram. Okay, and actually I'm going to call this a web diagram. So at the bottom, I have this sequence of thicknesses, which is 1, 2, 1, 3, 1, 4, and at the top it's 6, 4, 2. So I'm going to call this a web that starts at that sequence and ends at this sequence. So I guess I'll talk about this in a second. So okay, you kind of know what to expect here. So there's operations you can do with these diagrams. You can stack them horizontally next to each other. And you can also vertically stack them, assuming the thicknesses in the middle match up. So when I do this vertical stacking, right, so I can start with a web that goes from 5 to 2, 2, 1, and I can stack on top of it a web that goes from 2, 2, 1 to 4, 1. And when I'm done, I get a web that goes from 5 to 4, 1. And maybe you wonder whether there's any way to simplify such a picture, and in this case there is. I'll show you how that works in a little bit, but it turns out this works out to being 6 times just that split. Okay, so this rule, right, so making sure the middles match up, and then I can stack them on top of each other. Right, you should expect that this feels like something like a composition. So webs form a category. And so this category of webs, I don't claim any ownership over this definition. So most of the ideas here come from Kalters, Chemnitzer, and Morrison. Actually, Brundin, Ednova, Eisenbud, Eddinghoff, and Ostrich have a definition of a very similar category. John explained most of it to us yesterday. He gave himself a 2 out of 10. So it's a high bar, but maybe I can get up to 3. Okay, so right, so what is this thing? So this isn't exactly the same thing. John was working over the rational numbers, and he had this extra Q floating around, but it's kind of similar. So GL web, this is a k-linear monoidal category. So what are the objects? So the objects are generated by these string thicknesses. And then the monoidal product of objects is you just stack them next to each other. And so what comes out of that is that a general object is just a finite sequence of thicknesses, or a finite sequence of non-negative integers. So I'm going to jump back and forth. So the unit object should be like a string of thickness 0, which I usually don't draw and I usually omit, so that's also the empty word. So then morphisms. So morphisms are k-linear combinations of web diagrams. I should mention k here. For me, it's usually just going to be the integers, but it just needs to be an integral domain of characteristic 0. At some points, we'll specify some other fields that I want k to be. But integral domain of characteristic 0 for the most part. Okay, so that's kind of general morphism is a linear combination of these diagrams. We have some generating morphisms, which are these. Remember, I read from bottom to top. Chelsea read top to bottom, and that messed me up a little bit from bottom to top. So this is a split, and this is a merge, right? So you can take a string of thickness a plus b and split it into an a and a b string, and then I can also kind of do a merge going the other direction. And these are generators in the sense that I can build any web diagram by sort of horizontally and vertically stacking these in some way. The monoidal product is just horizontally stacking. This is something like a tensor product of morphisms. And then composition is vertically stacking. Right? So if you have two diagrams, f and g, to do f composed of g, you just stack f on top of g. Okay, so this is what the category is. I also want some relations to sort of simplify my diagrams. The first relation, this actually is a relation that holds in any monoidal category. There's nothing special about webs here, and this is the interchange law. So it says that if you have two different web diagrams on different strings, like a different set of strings, then you can move them past each other like this. And Ben Elias sometimes calls this robot arms, which has been very evocative to me. There's some other relations. You saw these show up in John's talk. Associativity, and John called that second one co-associativity, which is maybe a better word for it, but I'll just stick with associativity. And this is maybe another time to contrast what I'm doing here with how John presented this. So John included these crossings as a generator. I'm giving a slightly different presentation, which ends up being roughly equivalent to what John did, except I'm not using crossings as generators, which means I have a slightly different set of relations. So my set of relations includes this rung swap relation, which looks a little bit funny, but what this is saying is if I take so this is kind of like a ladder picture, and I split off a string from the left rung and merged onto the right, and then go the other direction. That can be rewritten as instead going from right to left and then left to right. And this is some sum. Okay, so that looks a little bit confusing. I'll come back to that relation in just a second. If you look at this sum, this looks like a great big infinite sum. If t gets big enough, these s minus t and r minus t's are eventually going to be negative. So anytime I see a diagram with a negative thickness, I just declare that to be the 0 diagram. And then strands with thickness 0, I usually don't draw them. So this rung swap relation has a special case when b is 0 and r is s. So when b is 0, I'm not going to draw this b string over here. In which case, the picture kind of looks like this. And if you look at the sum, that sum is non-zero only when t is equal to s. And what comes out is that this picture, or sort of split, and then I merge back, is just the binomial coefficient a choose s times the strand of thickness a. So this is sometimes called the knot-hole relation. So right, it's usually kind of written in this form, and if you really relabel your string lengths, it turns into this equation. Okay, so if I take, this is that picture I got before that I told you I was going to show you how to simplify. So if I take that diagram that I got before and I want to simplify it now using my web relations, the first thing I'm going to do is I'm going to say this is a split and then another split. So I can use associativity to do that splitting instead. But now I have one of these knot-hole things. Right, so it's a where I guess a and b are both 2. And then this relation lets me close up the knot-hole, and a scalar pops out. The scalar is a 4 choose 2, which is 6. So this is kind of how these reductions work when you're working with webs. So one of the things you can do once you have this knot-hole relation is you can imagine having a strand, and then you split it out into a bunch of thickness 1 strands. I call thickness 1 strands thin strands, and then merge them back together. And so if you look at this, this is kind of like having a little knot hole there that I could close up, and then you have another knot hole you can close up, and by induction you can show that this like explode into thin strands and then close back up is a factorial times just the thick strand. But what you should be thinking here then is that the thick strands are something like divided powers of thin strands, right? So the thick strand is like an a factorial times a picture that uses thin strands instead. And for this reason, webs frequently get used when you want to do like thin strand stuff, but over the integers, because you have this like sort of divided power thing built in to the diagrammatics. So in John's presentation, he included crossings as a generator. I'm defining them in terms of webs instead. So I'm defining the crossing to be this sum of ladder diagrams, right? So I sort of take some strands, drag them over to the right, and then drag them back to the left. Let's see, when this looks like an infinite sum, but most of the terms are going to be 0, just for a minus t. B minus t might be 0. Will be 0 if t is big enough. Okay, so this looks a little bit funny. This definition comes from looking at how like you can use the action of gln to give an action of the Weyl group on appropriate weight spaces. It's from Countess, Mr. Morrison. So when a equals b equals 1, it just turns into this formula. Right? You only have 2 terms showing up in this sum. When a is 2, b equals 1, it turns into that formula. So, right, it looks kind of complicated, but it's not such a bad thing to work with. And just to give you an idea of how you would calculate with these things. All right, so here I stacked the crossing, the 1-1 crossing on top of itself. So the 1-1 crossing is this thing. So I stack it on top of itself. And when I do that, my stacking operation is bilinear, so I sort of have to expand this bilinearly. And what you see is that when these two stack, it'll get that picture. And then I'll get two pictures where I stack kind of the identity on top of this merge split. So I got a -2. And then I add on, and I stack those two, the signs will turn into a plus, and I'll just get an identity. But now I have this knot hole relation that I completed the knot hole onto that diagram on the left. So I can close up that bubble, that knot hole, and a scalar of 2 pops out. So then these will cancel, and when I'm done, I just get the 2 vertical strands. And so if you take this crossing and you stack it on top of itself, you can use the relations to get that. This is just the 2 vertical strands. Some other relations that these crossing morphisms satisfy, and this works for all A and B. This is that relation that I just showed you, at least when A is 1 and B is 1. Let's see, you have a braid relation. This is a relation that says you can pull merges past crossings. There's another relation that's similar that you can use splits instead of merges, right? So kind of this picture drawn upside down. Let's see, and then there's also this relation that says if you put a crossing under a merge, it's sort of the merge undoes the crossing. The same sort of thing for a split. Okay, so these should look kind of symmetric groupy, these pictures. So Countess, Mr. Morrison have these ideas, the ideas of this theorem in their paper, although the first place that I could find this theorem written down in the quantum case was Tugendhauer-Vaz-Wedrick paper. And so it says that if you take this web category and you just look at thin strands, so strands of thickness 1, this 1 to the d for me means take a strand of thickness 1, d many times. And if you look at the endomorphisms of that thing, so this would be all webs that start and end with d many strands of thickness 1. This is isomorphic to the group algebra for the symmetric group, where the crossing of the ith and ith plus first string corresponds to the ith simple transposition. So this is maybe a philosophy in working with webs, is that if you just look at the thin strands. So here, this is strands of thickness 1. You should get back a thing that you're already familiar with. So in this case, just looking at the thin strands, we see the symmetric group. Okay, so that's the webs for GL at least. So then how is this related? Why am I calling these webs for GL? So these have some connection to representation theory of GLN. So GLN, right, so this is just the general linear Lie algebra over my ring K. It has a natural right module. I want to do right modules, as backwards as that feels to me sometimes. So right, I can take K to the n. I'm going to think about that as being row vectors. And I can take one of those row vectors and multiply it by an n by n matrix to get another row vector back. So this is the natural right module. It has a basis over K, given by these V1 up to Vn's, where just Vi has a 1 in the ith slot and 0 everywhere else. And then out of this natural module, you can construct a symmetric algebra, which is spanned by, actually has a basis given by products of these basis vectors V1 up to Vn. And it's an algebra where the rule is that if you do a Vi times a Vj, you can switch the order and get Vj times V. And this is a direct sum of symmetric powers. So then you also get these symmetric powers, SA. We're going to write SA for the 8th power symmetric power of V. So the 0th symmetric power, that's just the rounding. The first symmetric power is the natural module. Okay, so I just built a whole bunch of right modules for you, is what you should get out of this so far. Okay, now let's define a module category. And so I'm going to look at the category of right GLN modules of the form, let's see, so I'm going to write S, and then up there you should think about that A with a little arrow above it as being a tuple. So an A with an arrow above it is a sequence A1 up to AK. So if I write an S with one of these tuples up there, and what that means is that I'm going to take a tensor product of symmetric powers, where the tuple tells me which symmetric powers have to be taken. Okay, and then morphisms in this category are GLN module homomorphisms. So monoidal, right, it has a tensor product operation. You can tensor these modules and you get another module of that form. You can tensor the module homomorphisms. K-linear, the module homomorphisms are K modules. Okay, now the theorem is that for every n bigger than or equal to 1, so no matter what n you choose, there's a K-linear monoidal functor from this web category into the module category. On objects, it takes a sequence of thicknesses. Right, so the objects in GL webs, those just labeled thicknesses for my web diagrams, thicknesses of the strings. So this sequence of thicknesses is going to go to this tensor product of symmetric powers. Morphisms, right, so if the merge map from AB to A plus B, that should correspond to a module homomorphism from SA tensor SB to SA plus B. That's just multiply. I take a degree A element of the symmetric algebra and a degree B element of the symmetric algebra, multiply, I'm not getting an A plus B degree element. So the split map corresponds to something that's coming from a co-multiplication in the symmetric algebra. So what you do is you take a degree A plus B element of the symmetric algebra, and then you split it, and so you drag A of the things in your monomial off to the left, and B of the things off to the right. But then you sort of want to be as democratic as possible about this, so you sum over all possible ways to do this split. And then for a general web, you just extend monoidally. Yeah?
Do you care about the order, like preserving the order of the vectors when you split?
No, because it's symmetric, right? Or, right, I've got the commutativity of the vectors. Yeah, so I mean, if I had like some preferred basis, I would maybe want to rearrange them into my preferred basis. But. Okay, so we got this theorem. So what else can we say about it? So if you apply this functor to one of my crossing morphisms, right? So I should get a map from SA tensor SB to SB tensor SA. And this is just the symmetric flip map, right? So it takes two elements of the symmetric algebra and just flips the two slots that they're on. Flip tensor flip. If you just look at what happens on the strands of thickness 1, so on the thin strands, right? So the endomorphism algebras in the web category, we said we're just the group algebra with the symmetric group up to isomorphism. So I get, this functor gives me an algebra homomorphism from this endomorphism algebra to this endomorphism algebra. And that's the usual algebra homomorphism associated with Schur duality, which is known to be surjective, for example, if K is an infinite field. So for a general commutative integral domain of characteristic 0, fullness fails. But we can prove, for example, that it fullness holds, right? So this is the full functor, as long as K is a characteristic 0 filter. An experienced web slingers will know to expect that fullness is related to the existence of a certain Howe duality. I'll be a little bit more specific about what I mean about Howe duality in just a little bit. At least in characteristic 0, I haven't thought too much about the other case to see what the kernel looks like, but at least in characteristic 0, you can calculate the kernel of this map. And it turns out it's monoidally generated by a single morphism. So, which is to say that if you look at your web category, there's one additional relation you can impose in your web category, and then assuming you're in over a characteristic 0 field, after you impose this one additional relation on the morphisms, this functor becomes an equivalence of categories. Okay, so that's the connection between the GL webs and this module category. Any questions at this point? Yeah.
What is the other relation that you impose?
So at least, like I said, so I know what it is in characteristic 0. So what you do is you take, let's see, so I've got some particular n fixed. So then if I look at webs that start and end, so use d equals n plus 1 here. So then there is an anti-symmetrizer in that group algebra. And if you look at the anti-symmetrizer in the group algebra and you set it equal to 0, that's my additional relation, then you do get this equivalence of categories. Okay, so let's do some superalgebra. Okay, so what's a superalgebra? So a superalgebra is, or a superspace, this is just a Z2 graded K module, right? So it's a K module of E, which it comes with a decomposition into an even and an odd submodules. If you have two superspaces, V and W, you can tensor them together. Here I'm tensoring over my ground ring K to get a new superspace. And how do you decide what the grading should be on this tensor product? Well, so even tensor even is even, odd tensor odd is even. And then if you tensor an even with an odd or an odd with an even, you get an odd vector in this tensor product. So then a K superalgebra, this is a K algebra, so it already has a multiplication built in, which is also a superspace, so it has one of these decompositions. And the multiplication, right, which you can view as a map from the tensor product down to A, should preserve parity. Right, so this is maybe a fancier way of saying that even times even is even times odd is odd times odd is even. So some examples. So anytime you have a K algebra, you can put it in degree 0, in even degree, and you get a superalgebra. So in particular, I could take my ground ring K and just say that's going to be the even part of my superalgebra, and then the odd part will just be 0. So I can think about K itself as being a superalgebra. A non-trivial example is the Clifford algebra. And so the Clifford algebra, what you do is you take the algebra generated by a single element, which is odd. I'm going to call it C. And the rule is that C squares to 1. So this is a little kind of two-dimensional algebra where the odd vector squares to 1. So if you look at the classification of simple superalgebra, say over an algebraic enclosed field, This is not simple when you just view it as an algebra, but it is simple when you view it as a superalgebra. That's going to show up in a little bit. The zigzag algebra. So this is maybe a thing you haven't run into unless you've been reading math papers in a certain part of the representation theory world in the last few years. So the zigzag algebra, this is a quotient of the path algebra of a quiver. Right, so this is like a type A quiver where I doubled all my arrows. I have arrows going forwards and backwards now. So I look at that path algebra, and I impose some additional relations. So one relation I impose is that paths of length greater than 2 or 0. Right, so I can't go from here to here, for example. That would be 0. Length 2 paths, or I guess that would be greater than 2. Length 2 paths which are not cycles are also 0. And then any 2 cycles which are based at the same point are equal. Right, so this cycle and this cycle, those are the same element of the zigzag algebra. But this is a superalgebra. How do you make it into a superalgebra? You just look at the length of a path mod G. So the odd elements of the superalgebra are just the length 1 paths. And then the even elements are the cycles, and the length 0 paths, which is just like stay at a vertex. Okay, so that's some superalgebra. The next thing I want to tell you about is these deformations of webs, which is sort of the main topic of this talk. Any questions at this point? Okay, so what's the big idea here? So the idea of doing superalgebra deformations, this has appeared in the literature before. Right, so for example, if you take the symmetric group, right, you can think about the symmetric group as kind of being presented using diagrams. And if you glue elements of a superalgebra onto the strings, you get something called an affine wreath, or a wreath product algebra, which has appeared several times before. There's other examples of this. If you take the degenerate affine Hecke algebra and you sort of deform it using a superalgebra sort of in a similar way to what I'm about to do, you get an affine wreath product algebra. And so there's other versions of this involving Heisenberg. So the idea to do what we're describing here, which is to take elements of a superalgebra and glue them onto a web. This isn't new, but or the idea to glue elements of a superalgebra into diagrams is not new. But doing it for webs is kind of the new thing. Okay, so what do we do? So you take a web, so a GeoWeb, picture like that. And then I'm going to glue some coupons onto my web. And the coupons are coming from my superalgebra. And there's some restrictions. So this is a string of thickness 1, so that's a thin strand. And you can glue any element of your superalgebra onto a thin strand. So any element of your superalgebra is allowed to be a coupon on a thin strand. On these thicker strands of thickness at least 2, the rule is that you're only allowed to glue even elements of your superalgebra onto those thick strands. Okay, so more formally, what is this web A category? So A is a K superalgebra, and so it has an even and an odd part, and it's an algebra. Web A is a monoidal supercategory. Let's see, monoidal tensor product operation supercategory means that the modules are K superspaces, or the morphism spaces are K superspaces. So they have a Z2 grading. Objects, so the objects are the same objects we had before for ordinary webs. They're just sequences of non-negative integers. Morphisms, so we still have these generating morphisms, these merges and splits. So as a consequence, I can build any GL web picture in this new web category because I have these morphisms still. But I have some additional morphisms. And my additional morphisms are these coupons. So we sort of have 2 types of coupons. So on strands of thickness 1, I'm allowed to glue any element of my superalgebra onto a strand of thickness 1. So those coupons are my generators. But then for thicker strands, these coupons have to be elements of the even subalgebra. Okay, and then this is a monoidal supercategory, so morphisms are supposed to have a Z2 grading. These coupons could be even or odd. They'll be odd exactly when I'm gluing on an odd morphism or an odd element of my superalgebra. Okay, so then, right, I've given you objects, I've given you some generating morphisms, and then I need some relations. So here we're subject to the same relations that GL webs were before, right, like rung swap, associativity, things like that, plus some additional relations involving the coupons. So actually, before I talk about all the coupon relations, I should mention, for those of you that haven't worked in monoidal supercategories, before in just a monoidal category you had right, interchange law, robot arms. Now I get something like super robot arms. So super interchange law, which says that if you have an odd morphism on one string and an odd morphism on another string, if you change their relative heights, a sign pops up. So there's some subtlety involving working with super things where I spend lots of time chasing signs around. This is just either a feature or a bug of working with superalgebra. Let's call it a feature. So what other kinds of relations do we have? So if you take a coupon labeled by the identity element of my superalgebra, so labeled by 1, I can remove that. If you take, let's see, this is written a little bit tiny, but in there, that's a scalar, so an element of k multiplied by the element f in my superalgebra. So if you multiply by a scalar in your coupons, you can pull the scalar out. I get raised to the thickness of the string power, and then leave the rest of the coupon alone. Let's see, there's this coupon collision relation maybe, right? So if you have two coupons, F and G, you can slide them together. And when you slide them together, you just multiply F and G. There's this funny relation over here, which says that if you add two things together on a coupon of thickness A, you get the sum of knot holes, where on the left, you're putting F's in there, and on the right, you're putting G's in there. By the way, this, it's not obvious yet, but this is symmetric in the sense that I could have put the F's on the right and the G's on the left instead. I would have given you the same picture, or the same morphism. Right, so for example, I'm a string of thickness 2. If I put an F plus G in there, I get a sum of 3 separate terms. The F on a string of thickness 2, a G on a string of thickness 2, and then this knot hole. Or the F and G are both on strings of thickness 1. The odd knot hole relation, this maybe looks a little bit funny. So take a strand of thickness 2, split it into thickness 1 strands, glue an odd element from the algebra, same element on both sides. So this is, like I said, a little bit hard to see. Those two coupons are the same odd element from the algebra. And we're declaring that that odd knot hole is equal to 0. I'll show you why that is in a second. Then some other relations. So assuming, I guess, F here needs to be an element of my even subalgebra in order to have it on this thick string in the first place. But if I have an F on a thick string, I can slide it past a split to put it on the thinner strings. Same thing for splits. And then there's this kind of intertwining relation, which says that you can pull coupons past crossings. Okay, so where's this odd knot hole coming from? Let's see. So if I take the odd knot hole, right, so there's an F on both of those spots. We had this relation before that said crossings get gobbled up by merges and splits. So I can put a crossing there. And if I put a crossing there, then I can use this relation that says coupons move past crossings. Right, so that F, I can slide it down, and that F, I can slide it down. And if you pay close attention to what's going on, right, so you get an F here, and an F here. And if you pay close attention to what's going on, let's see, so maybe I should have drawn this so that one F was slightly above the other. So let's see, this one would now be lower than this one. we do it like that. Now this merge can swallow up the crossing. Let's see, so now that one's lower, that one's higher. Oh, and then this is the same thing as that odd not null that we started with. So the point is that when I do this, these are all equal to one another, but I change the heights of F. So that means that this diagram is actually equal to its negative using the super interchange law. So 2 times it should be 0. And we don't want any 2 torsion in our category, so I better set that thing equal to 0 to avoid having 2 torsion. Okay, so what are some special cases? So if I choose A to just be my ground ring K, this web A thing that I'm constructing, this deformed webs, I'm just getting the geo webs that I had before. Yeah?
If your coupon is 0, the strand disappears.
Yeah. Yeah, so I guess a coupon 0, I could use this relation that says you can pull scalars off coupons, and I just get 0 times my diagram. Yeah, so if A is just my ground ring, I get GL webs back. If A is a Clifford algebra, so this has the one odd generator that squares to the identity. In these constructions, we can show that our constructions are the same as what's called the Q webs category. So these are webs associated with a type Q Lie superalgebra. So these Q webs are originally defined by Brown and Kujawa, but and then there's a quantum version of it that I worked on with those two also. Okay, so if you look at our paper, we put it up in January. You'll see that the constructions there are a bit more complicated than what I'm showing you here. So actually, in our paper, we define these web A's not just for a superalgebra, but for a locally unidal superalgebra. Right, so John's been talking about these. So you have like these favorite idempotents. And if you look at our paper, there's this extra complication given by, we have to color our strings by these idempotents. Right, so each of our strings has a color given by an idempotent. Right, so for the sake of clarity, I'm not going into detail. Okay, so let's see, what sort of things should you expect? Well, I said the thin strand version of a web category should be a thing that you already recognize. Right, so if I take endomorphisms of webs, or endomorphisms of thin strands, right, so 1, 1, 1, 1, 1, D many times. Before I added the A's, I had just the group algebra for the symmetric group. Now I've got something like the group algebra for the symmetric group, but with some coupons glued onto it. And this has a name already. This is the Reed product algebra. Right, so we can show that endomorphisms of kind of thin strands are Reed product algebras in our setting. Okay, any questions at this point?
Is there any reason why the coupons on the 6 strings have to be even?
Have to be even only. So if they were odd, it kind of comes from this fact that I've already declared that odd not holes are 0. So if you take that relation and sort of look at what would have happened if I had odd coupons on thicker strands, you could show that those also would have been 0. Right? So odd coupons on thick strands would have ended up being 0 anyway, so we just aren't allowed them. Okay, so let's do some representation theory now. So let's view the matrix algebra, MNK. I can view this as a superalgebra just by putting in even degree. And then I can tensor that superalgebra by another superalgebra, A. And now I just get matrices with entries in A. So this is a superalgebra. It's spanned by, these are kind of like matrix units where the RS entry is some element of my superalgebra and I get 0 everywhere else. Okay, and then these matrices are an associative algebra. So I can do something like I would do for normal Lie algebras. And I can use like commutators to get a Lie algebra. But now things have a Z2 grading. So I don't get a Lie algebra, I get something called a Lie superalgebra. So the bracket here is you multiply the matrices in both directions and subtract like usual. The only sort of weird thing that's going to happen is that if you do the bracket of 2 odd things, another sign pops out, and then instead of subtracting, you add. So GLN A, these are matrices with entries in A. This has a right module, which is row vectors with entries in A, where these vectors are spanned by these vectors of the form VIF, where you just put in the superalgebra element F in the ith spot and 0 everywhere else. And then there's this formula for how things multiply, which is kind of like how vectors multiply by matrices. In the usual case, the only weird thing that happens is, right, my matrices are decorated by elements of a superalgebra, so are my vectors. You just multiply the signs. Okay, in this setting, you have a supersymmetric algebra instead of just a symmetric algebra. The difference is that if you interchange two odd things, two vectors which are decorated by odd morphisms, a sign pops out. And as a consequence, if you take like a VIF where F is odd and you square it, it's equal to its negative because of this sort of switch around relation. So we're actually going to mod out squares of odd vectors, right? Because they're equal to their negative, and I'm trying to avoid torsion, so I should mod these out to avoid two torsion. Okay, and then you also get these supersymmetric powers, SDV, where D is any non-negative integer. At one point, it occurred to me that I really should be leaning into like comic book language in this talk. So, right, we've got webs. I dropped web slinger a little bit ago. Supersymmetric powers, symmetric superpowers. Okay, so what modular homomorphisms do I have now? So I still have this like multiplication modular homomorphism, which takes a degree A thing and a degree B thing, multiplies to get a degree A plus B thing. I still have a split map. Remember the split map, the way it worked before is you take a degree A plus B thing and you split it into an A and a B. The only weird thing that happens is this splitting process might move some odd stuff past some other odd stuff. So you have to sneak some signs in. It's not a big deal, but there's a sign that appears in these formulas. And then, right, so GLN A is acting on the right, but my vectors are have entries in A. So then I can still multiply on the left by stuff from A to get modular homomorphisms because GLN A is acting on the right. So on V, we left multiply by any element of my superalgebra. And then on a symmetric power, where the power is at least 2, we also let ourselves multiply by even elements. If I try to multiply by an odd element, I can use this relation that, let's see, what do I want to say here? Yeah. For odd stuff, things get a little bit messy, and it's coming from this like torsion and these products of odd things, anti-computing, and things like that. So it gets a little bit messier in that case. Okay, so we're only going to multiply by even morphisms in this thing. Okay, so here's our theorem. It's that for every n bigger than or equal to 1, there's an asymptotically faithful, I'll tell you what asymptotically faithful means in a second, monoidal superfunctor from the web category to the modular category. Right, so it sends a tuple A to a tensor product of symmetric powers, just as before. Let's see, the merge diagram goes to this multiplication map merge. The split diagram goes to this sign splitting diagram. And then the coupons go to this left multiplication modular homomorphism. Okay, so asymptotic faithfulness here, it's used to prove a basis theorem for morphism spaces. So asymptotic faithfulness, what this is saying is if you give me any morphism in this category, we prove that if you make the n here big enough, then the image of whatever morphism you had here ends up being non-zero. Right? So this map, there's no reason to expect this functor to be faithful in general, but if you make the n big enough, it'll be kind of faithful in any morphism you want it to be faithful. It'll be non-zero in any morphism you want it to be non-zero. Okay, and we use that to prove a basis theorem for the morphism spaces here. We also get this algebra homomorphism from, right, this is kind of the analog of Schur-Weil duality in this case. So the thin strand algebras here are these race product algebras. So they map it, you get an algebra homomorphism into the GLN-A module homomorphisms from this tensor space to itself. And then the fullness of this finite thing is closely related to the existence of a Howe duality for GLN-A, and it doesn't always hold. And I'm looking at the time, and I think, I'm not going to explain the Howe duality stuff. I will just say that we do have a theorem that at least gives us one special case where we have fullness. Okay, so assuming that we're working over an algebraically closed field, so my K is algebraically closed, and the characteristic is 0, and the algebra A that I'm sort of using to glue on my coupons is a semi-simple superalgebra. So semi-simple superalgebra, there's a classification of these things. They're all isomorphic to products of either ordinary matrix algebras or matrix algebras where the entries are elements of this Clifford algebra. These are sometimes called type Q matrices, where you put Clifford algebra in for your entries. So the algebra homomorphism in this specific setting, going from the Reith product algebra into this endomorphisms of tensor space. This is surjective for all n and d in this case. There's the Howe duality that holds in this setting, which the Howe duality, like I said, I didn't explain what it means. What it's saying is this is the natural module for GLM, and this is the natural module for GLN, and I'm tensoring them together there. So both of these act on this space. So then they also act on symmetric powers of that space. And the Howe duality in this setting just means that they generate each other's centralizers when they're acting on this space. So in this setting, you get this multiplicity-free decomposition where that, as a bimodule, this decomposes as the direct sum of tensor products of simple modules for GLN-A and GLN-A. And this indexing set is something like Hooke multiplications, but it kind of depends on how your algebra breaks up as a direct sum of semi-simple product of simple algebras. Maybe this is worth saying that in this case up here, when A is just an ordinary matrix algebra, this is just Schur-Weil duality. When A is one of these like Clifford matrix algebras, this is called Sergeev duality. In this setting down here, if A is a ordinary matrix algebra, this is ordinary Howe duality, classical Howe duality. When A is one of these Clifford matrix algebras, this is a result. This recovers a result due to Wei-Shang and Xu-Yi-Chen. Okay, but so what you should think here is that this result sort of recovers some previous results in special cases. And then in that case, this functor is also full. Kind of having this duality is somehow related to having fullness. Okay, the other thing that I wanted to mention is these Schurifications. And so, question of Muth defined, so what you do is you take a matrix algebra with entries in a superalgebra, tensor it by itself d many times. So the symmetric group can permute these tensor factors, so we can look at invariance. Kujawa Muth called this the generalized Schur algebra, or this is an example of a generalized Schur algebra associated to A. Generalized is the classical Schur algebra because, for example, if A is just your ground ring K, this just gives you the Schur algebra. So this is like a superalgebra deformation of a Schur algebra. So it turns out this SAND thing that I defined up there, it doesn't quite do everything that Kujawa Muth wanted it to do. So for example, if A has lots of nice properties, this SAND didn't have lots of nice properties also. So what they did is they chose some little a inside the even part of capital A. And then they define a subalgebra of this SAND thing, which depends on that choice. So it's given by scaling some basis elements in this thing. The construction of the point, though, is I'm not telling you exactly what it is because it's complicated. And then one of the main uses for these things, these Schurifications, TA and D algebras is if you plug zigzag algebras into these constructions. This is like that quotient of the path algebra that I showed you before. FCU in question showed that these Schurified zigzag algebras are marine equivalent to rock blocks for the symmetric group. So these rock blocks for the symmetric group are, take the group algebra of the symmetric group. If I'm not working over a characteristic zero field, it doesn't necessarily decompose as a product of matrix algebras. The blocks it decomposes into might be kind of complicated. Rukier and Chong Kesar, though, sort of classified a nice set of blocks called rock blocks. And then it's known that every block for the symmetric group is derived equivalent to a rock block. So if you want to do representation theory for symmetric groups, you need to understand all blocks. If you only want to do things up to derived equivalences, then you might as well just understand rock blocks. So then the point of this theorem is that if you want to understand rock blocks up to marine equivalence, you just need to understand these purifications of zigzag groups. Yeah?
Wait, this element A is, what's it say? Paths?
Oh, these are just the length zero paths inside
So you choose anyone?
the path algebra.
You choose
Oh,
anyone?
this little a is a subalgebra, and it's a subalgebra of all length zero paths. Yeah. Okay, so the reason, I'll just give you the upshot. The reason that this is, right, so there's 4 people working on this project. Muth was involved in defining these TA and D algebras. And the reason he got in on this project is he got really excited because you can, instead of defining these TA and D algebras using these like symmetric group invariants, and you go to a subalgebra, which is a little bit complicated, you can just build them using these webs instead. So for the sake of time, I'm not going to go into detail, but the point is that these constructions, you can both recover the SAND and the TAND algebras just by looking at morphisms in our webs. Yeah. So this kind of, the web category give you a more easier to work with definition of these algebras. Okay, future directions. Maybe I'll just throw some stuff up. So this is kind of, hopefully this will be done this summer. We're working on it right now. This is one of the things we talked about at our recent meeting. We're also working on defining affine versions of these things, right? So where you kind of put some polynomial dots on your diagrams instead of just only putting coupons on your diagrams. And then associated with these things, we have like cyclotomic quotients. The thin strand, in this case, corresponds to affine Reith product algebras that Savage defined. And then you can also get cyclotomic Reith algebras out of these constructions. And then kind of the reason we're working in this direction is there's a whole bunch of marine equivalences that we're sort of expecting to fall out of this story. Right, so in the ordinary deformed A deformations of webs, or these superalgebra deformations of webs, we get these Schurifications of A, which are marine equivalent to rock blocks. But we think we can get marine equivalences with other things like rock blocks for Ricci-Koika algebras, or maybe rock blocks for the spin symmetric group and things like that coming out of these marine equivalences. That's it for me. Thank you very much.
Yeah, I have one.
Yeah.
So we just put out a paper on quantum Reith products.
Okay, yeah, I saw this.
Yes. So is there do you think there's going to be a web interpretation of this quantum Reith product?
Yeah, so I mean, the story then would be that there should be a quantum version of these A webs, which for the thin strand version would be something like your quantum Reith product algebras.
So the quantum Reith product actually recovers the Savage construction and then the Schurification and all these other constructions that you mentioned. So.
Okay, yeah, no, so this would be, right, I think if you wanted to do the quantum version of the story, I think your paper would be like the first thing to look at is like the base case where you're doing thin strands and then try to figure out how to do thick strands. I've learned in a couple of situations that quantum stuff is always harder than I'm expecting it to be. Right, I mean, maybe this would be very difficult to do, but I think that should be a promising thing to do. Yeah?
Can you go back to the previous slide? What do you mean by the imaginary KLR?
So imaginary KLR algebra, right? So there's these KLR algebras, And you can associate KLR algebras to, I don't know, Dicke diagrams. So if you look at an affine type A Dicke diagram, you have this imaginary root. And imaginary KLR is like some sort of quotient of this, maybe like a subalgebra of the KLR algebra in this case. Kujawa and Muth have a lot of work on this. But where you're expecting that the affine, if you take the affine web algebra, it produces webs with dots, and plug in zigzag to these constructions, we should get something that's really equivalent to imaginary.
So like R alpha, modules over that categorified like that using the alpha weight space. So here, I guess by imaginary KLR you mean like imaginary roots?
Yeah, so I think, let's see if I can get this right. So I think the alphas you use are like sums of the imaginary root. They call these things like C and delta, right? So you would just add a delta.
So for your fullness theorem, you needed algebraically closed and characteristic 0.
Yeah.
Is that honest, or do you need is it like Schur's lemma that you need, or something like that?
Oh,
why?
let's see. I think, yeah. So, what do you mean by Schur's lemma? It's like to hold in the modular category, or
No, I guess why do you need algebraically closed and characteristic 0?
So algebraically closed characteristic 0. So characteristic 0. One of the things I mentioned was that the thick strands are like divided powers of thin strands. So if you're in characteristic 0, you can kind of clear or divide appropriately. And what that means is if you know things are true in the thin strand world, you can like bootstrap up to the thick strand world really quickly. So then when you're characteristic 0, it kind of reduces to checking fullness on the thick strand or the thin strand version, where you're just doing wreath product algebra mapping to this tensor space. And you want that to be surjective. And then I think algebraically closed is probably being used. I'd have to look at it again, because then we have a classification of what the semi-simple superalgebras look like in an algebraically closed field.
Okay, yeah, thank you.
Yeah.